Hey guys, welcome back to another video. Today we're going to be rating mathematical, scientifical, basically just symbols. Basically math symbols. Some of them are obviously going to be popping up in physics. You know, we got our basic Greek letters. Then we move on to some basic like physics letters. We go to some mathematical number theory operators, and then just some basic symbols for some units of energy and other types of things, and then some mathematical notation. And we'll get into it. We also see some symbols here from quantum mechanics. So let's get into it. Let's get started with alpha. All right, and now alpha, you know, it's a nice Greek letter. We get it in math, we get it in physics. It's a pretty good all-rounder. It's the first Greek letter you learn, but I feel like there are so many better ones. I think it's just, I'm going to put it in pretty cool. I think there are some better ones. Now, beta is better than alpha. I could say that right off the bat. It looks better, it sounds cooler. It's also introduced like right at the same time when you're in geometry doing triangles. It's beautiful. But now that I think about it, there are so many other letters that are also good that I'm just going to put it in A+. Now, gamma, I'm sorry, gamma, but it sounds cool, but it just is such an ugly letter to write. And it's used way less than alpha and beta, and people kind of forget about it. I feel like more people know delta than gamma, and it's just kind of overrated. I'm sorry, guys. I'm putting it in C tier. Delta. Now, I don't like the capital delta sign. I do love the lowercase delta triangle. For that reason, I'd have to put it in overrated as well, but it's not horrible. But because the lowercase one is good, I'm not putting it in mediocre. So I'm just going to put it in overrated, so it's going to be C tier. Now, epsilon. Oh, boy, that's a tough one. Well, you see, epsilon, it has its uses. You do see it sometimes in math, but it's kind of forgotten. It's sort of ripping off E, and, I mean, it's just kind of bad. I don't like it. I'm putting it in mediocre, D tier. Now, zeta. Oh, boy. I mean, I like writing it. I don't like the way it's printed out, but I like writing the zeta letter on my iPad when I have a pen. The Riemann zeta function, super cool functions, super interesting. Was just watching and researching a bit on it today. I like zeta, but I don't think that it's known. I think it's probably the least known letter, or one of the least known letters in the Greek alphabet, because it really has absolutely no use unless you're working with zeta functions. But I'm going to put it in normal. Alright? So B tier. Or C tier, actually. I'm sorry, guys. I forget that. B tier is already pretty good. Now, eta, I guess you would call it eta. People say theta and eta. Okay, I guess eta would not be right. Eta. Ada's weird, guys. I mean, it sounds like an E, but then they write it like an N, so it would fit more than nu, but then nu looks like a V. It's just sort of a mess. And I mean, you don't even use eta that much. It's kind of just like this secondary angle that you never really talk about. It's going in trash. I'm sorry, guys. F tier. Now, theta. Oh, boy. Theta is the GOAT. I wish we would use theta instead of alpha for angles, because theta is just so beautiful. I mean, and there just happens to be a category for beautiful. It's going right up there in A++ tier. There you go. Iota. Now, I have some friends that like iota. Me, myself, I have nothing against it. I think it's a wonderful name. I think it's such a beautiful name to pronounce. But I've not seen iota at school. I have not seen it in any of the research that I've done. I haven't seen it in physics. Now, I'm sure there's a field where it is, but I'm not going into thermodynamics or whatever, and I don't really care about it. So, unfortunately, iota, you are mediocre. Just like epsilon. All right, kappa. Kappa is nice. I'm not gonna lie to you. It's a cool letter. The K is nice. It's simple. It's easy to learn. I think I'm gonna put it in normal. It's now that I think about it, zeta must go normal as well, because kappa cannot be alone in here. And I've never really used kappa, but I mean, just the fact that it's a K, it's called kappa, and it's easy to remember. It's just so useful to learn. Now the big boss, lambda. Now, ladies and gentlemen, lambda is my favorite Greek letter, and let me tell you why. Number one, lambda looks so cool. You just draw, it's just a vertical line and then another vertical line. Beautiful. It looks cool. The name is cool. It sounds advanced, modernized, industrial, futuristic. And the best part is the greatest video game of all time, Half-Life 1, uses the Lambda symbol as its logo. The Lambda complex in the Black Mesa Research Facility is Lambda. The Lambda complex. Lambda is the greatest Greek letter of all time, legendary S+ tier. You can't tell me nothing about it. Next up is Mu, or Mu. Now, Mu is a great letter. There's a lot of jokes on the internet. You're going like, mew, mew, mew. You know, you're saying Mew because it's like a mouse, like a cat. So I think it's very nice. I'm going to put it in underrated because I think people don't know enough about Mu, but it's a very nice letter. I was using it. We use it all over in physics. We've been using it in random matrix theory. Quantum chaos Mu is used all over the place. Statistics, for distributions. I mean, Mu is just a wonderful letter to have. Nu, unknown. Bro, who uses nu? Look at it, it's horrible. You got a V. Why V? Then it would be Vomicron or Vu. But no, they say nu. Why didn't you take the N from Ada and put it for nu? That would make more sense, but no. So that's going at the bottom. Now Xi. Now, do you guys notice that Xi looks exactly like Zeta, except it looks even more like Zeta, but it isn't Zeta, and it looks like Epsilon, and I mean it's horrible, and it looks like an E, but it's an XI. Just absolutely atrocious. They could have just used an X. Like for Chi, why didn't they use the X for Xi when it's Xi? It's like so stupid. Trash. It still looks so nice, so I'm not putting it in unknown, but it's trash, because why would they do that? Omicron. I'm going to put it on the same level as Kappa, easy to remember, it's the same as the name, it's unique so you can remember it. Now we got the big boss, Pi. The Pi's a goat. We all love Pi. And you learn it already in 6th grade. You know it. It's magnificent. S tier. Rho. I love Rho. I find that the way I write Rho is so much better. People like to put a little weird stripe at the bottom, but no, I like to just draw a circle, let go, and then put a straight line down. So you can sort of differentiate it from my regular P, which is just one intact line versus a circle and then the line. Rho is so nice, beautiful. I love it. Sigma, you know the sigma is the GOAT. We use it in math. I like the uppercase one, magnificent. If you've ever written a sum, you know the uppercase sigma, the one that looks sort of like a crocodile's mouth or whatever. It looks beautiful, magnificent. It's going in S tier. Now Tau, I don't know. But, oh, okay, now we're getting constants. But, okay, we're getting constants. But what are these little things? Or, what? Okay. Okay, oh, I see. Okay. I thought Tau was for that. Alright. Tau, it's alright. I'm putting it in mediocre. You know, I'm going to put it in the same as, I'm going to put it in overrated a bit. Because I just don't think they're as cool as Omicron, Kappa, and Zeta, but it's easy to remember, and if it's easy to remember, I like it. Upsilon, I think it's a great letter. You can remember it, but it's just sort of like weird. It's like, why when we have epsilon, you know? So I'm putting it in the same level as epsilon. Even, because people get confused. Phi, the GOAT. The GOAT. The GOAT. It's not as good as Lambda, but it's right up there. Phi is going in S+ tier. You know we love it. We love Phi. We love Phi. You know, you got Phi in your wave functions. You got Phi when you're writing your Schrodinger's equations. You got your Phi when you're doing your Ket notations. Phi is just everywhere. When you're Dirac notations, you know, you're doing your Kets everywhere in quantum physics. You're trying to show superpositions in mathematical notation. Phi is going to be there. Phi is showing you the quantum states. Beautiful letter, right up there with Lambda. Nothing else I can say. Now Chi. Now Chi, again, is going right next to the Xi because it's like why? Why Xi? Why Chi or Chi or whatever you want to call yourself? No. Next up, Psi. Psi is going in unknown, and the reason why is that Psi looks exactly like Phi, but it sounds the same, but it's completely different, and they always confuse me, and I don't like it, and now I'm afraid that I think Psi is actually the one in quantum physics, and now I've gotten it confused. Am I stupid? I think I've just mistaken it again. That's how bad it is. Yes, Psi is the quantum one, and Phi is going down here. At least I think. Let's ask Google. Hey Google, which Greek letter is used to represent quantum states? Psi. Exactly. Look how stupid I am, guys. I already messed it up again. That's how confusing it is. That's why phi is going in unknown. Or F tier, apparently. Unknown is not the worst. So then, there. Omega, wow. Omega. Now, I think the Omega is great. I think it's a great letter. I think I'm going to put it here here next to mu. I think it's just great because, you know, alpha and omega, the beginning and the end, I mean, it's got some aura to it. So, you know, we're going to keep it there. Now we're moving on to our physical constants, all right? Number 1, the speed of light, c, going absolutely here in pretty cool. You know, a fundamental constant in special relativity, knowing that the speed of light is constant, one of the biggest breakthroughs of the 1900s, just beautiful. The golden ratio, again, absolutely amazing. I'm pretty sure, I don't know if the golden ratio is written with this, like with the symbol. I've seen it with another symbol. But in any case, golden ratio, a beautiful ratio. You know, you got your 2 lines, you cut them up, you divide them, and yeah. I mean, it's nice. People say it's a top 4 mathematical constant. I don't think so. I mean, it's difficult to explain to people what the golden ratio really is. I'm putting it in normal, though. Now, Euler's constant, all right? And now, people get Euler's constant confused with Euler's number, and what you need to know is there's a difference. The Euler constant is also known as the Euler-Mascheroni constant, and it's written as gamma, as you can see right here. And it's a number that pops up when you compare 2 things. When you take the harmonic series, which is just 1 plus 1/2 plus 1/3 plus 1/4 recurring all the way over, and the natural logarithm. And the constant is defined as when you take the limit as n approaches infinity of the harmonic series minus the natural logarithm of n. So it's going as n approaches infinity, right? So this is Euler's constant. And I mean, it's all right. It's not too good. I don't really like it. We're going to put it right here in normal. Planck's constant, an absolute goat. If you need to look at small things, you need Planck's constant. Underrated. We're going in A tier. Reduced Planck's constant, that's going straight to trash because nobody cares about that. No one's ever heard of that in their life. Vacuum magnetic permeability, again, I don't like this one because we don't like anything that has to do with magnetism over here. We are relativity, quantum mechanics, and mechanics bros. And mathematics bros. We don't do none of this electromagnetism. We're not electrical engineers. We don't care about thermodynamics. We care about mechanics, quantum physics, and relativity. Let's continue. Vacuum electric permeability, right up here in trash. Gravitational constant, ooh, now we got a good one. 6.67 times 10 to the negative 13th power. I'm not sure if I got that right, but that sounds about right. Straight in A tier. It's beautiful. You need it for your gravitational equations for Newton. You want to calculate how strong the pull is between 2 objects. You need that gravitational constant within the equation. Take it divided by the distance squared. You know it's a must. Coulomb's constant. Another nice constant. I would put it in normal tier. Elementary charge. Now, I would say that the elementary charge is useful, but not many people know about it. And it's pretty boring. So it's going in overrated. Now, what is this? The inverse fine structure constant alpha is approximately 1 divided by 137. Unknown. Don't know what that is. Now, the mass of an electron, I am going to say it is pretty cool. Or just underrated. And the reason for that is because it's so small, it's basically irrelevant, and we don't even need to calculate it when calculating the molar mass for atoms, because it's just so insignificant, and that's what makes it so nice. Proton mass, I'm going to say normal. I think it's great. You know, you need it in your chemistry. You know, you got it. But after you get your molar mass, you got to count it, multiply it by Avogadro's number, you know, to get your molecules, and yeah. Avogadro's constant. Now, I'm going to say that it's kind of weird. Teachers don't really explain to you what it is at the beginning, so I'm going to put it in overrated, just because I feel like it could be explained better. The molar gas constant, mediocre, nobody cares about it. And Faraday's constant, again, mediocre, nobody cares about it. Now we're getting to mathematical notation. Now, this is interesting. For any of you who've been writing proofs, you will know that this is going to be fun. Arrow vector, firstly. I don't like it really because I felt like when I first got introduced, no one really explained what the arrow meant. You've been doing it for years. Obviously, when you write your vectors, you gotta have your arrow over it. I find it kind of annoying, so I'm gonna put it in overrated. Bold-face vector, I like this one. Most preferably, I like it when you just write it in brackets, like vertically down. But bold-face vector is also nice. I'm gonna put it in normal. L variant, I'm gonna say it's very nice. I love using the L variant because it's just a simple way of making sure that this is an L, not a capital I, and it's like a special L. I'm going in underrated. Beta variant, unknown. Who has ever used the beta variant? I have no clue. Now the epsilon variant, I'm gonna also put that in normal. I think it's been used a lot. I use it sometimes whenever I need to signify something, and yeah. Now the theta variant is absolute trash. I mean, who uses this? This is disgusting. Pi variant, this is even worse. I mean, this should be a trash F-. And kappa variant, I've never seen this in my life. This is the rho variant I'm talking about. The disgusting rho. Absolute trash. The sigma variant, again, trash. Now this phi variant, I like it. I like it a lot. This is what I usually see the golden ratio being written with. That's why I was confused when I saw that the golden ratio was written as a regular phi. Usually we see it as phi variant, and that's just why I was a bit confused. Now, the time variable, I think it's nice. Multivariable algebra is always nice, multivariable functions. I would like to see a little bit more multivariable calculus being introduced in high school. I don't see enough of it, but other than that, I think it's great. I, the imaginary unit, magnificent. Top 3 mathematical constants after Euler's number pi comes I. Great. And now we're getting to our mathematical operations. Equals, a wonderful sign. Pretty cool. It's nice. Sometimes people get it confused with equivalence, but it's equal to. Not equal to. I'm going to put it in overrated. It is not used enough. It is not used enough to be very goodly rated. We just use it sometimes, very, very rarely. At the very end of a proof. But it's so not used. You could just say this is not equal to this, and it would just be fine. Plus, honestly, I don't like plus. It's most of the time in math we're multiplying stuff, and so when you see plus, and all of a sudden you cannot distribute, you cannot divide, you cannot just do stuff on both sides because you have addition, you can't use power rules, it's just super annoying. So adding and subtracting, you're going down in mediocre. Multiplying, at least this time symbol, I would say it's normal, just because eventually as you have more variables, you just tend to write the variables next to each other. You're not doing times, you're not doing A times B times C, you just say A, B, C. And so it's kind of becomes redundant after a few weeks, after a few years, but yeah. Now this divide symbol, absolute garbage. Never use it. When do you ever write this? Never. Now we get to the real operators, really. Less than. So, firstly, these are kind of the same thing because you could just switch the letters that are there around. So, I don't really see how you can even say that this is less than. I guess the first is less than the right. Mediocre. I don't like them. I just find them super annoying. When you have one of those greater than equations, it's just so annoying. You move something, at the end you don't even get an answer. You just get around a range of what it could be, and it's just kind of stupid. Less or equal to. Now, I think these are actually much nicer, because they give us at least some hint of what the answer could be equal to. When I see this, it's often very close. It's going to be within 1. But whenever I see greater than, it's greater than, or it's less than 1 billion. And I'm like, great, what am I supposed to do with that? But when I say it's greater or equal to 0.005, I'm like, okay, I should be close, you know what I mean? In any case, root. Now, the root is nice. It's a staple, but I don't like the way it looks, so I'm going to put it in overrated. I just find that we should have found a cooler symbol for the root, because at least the one that is written here looks disturbingly ugly. Now, caret. Now, caret is alright. It looks kind of like a roof, it's kind of cute, but I feel like it just doesn't have as much aura as the other symbols. For that reason, mediocre. If. Now, these ones that are here are weird, because these are different follows. What this usually means is it follows that. So, A is squared, it follows that. A is even. In that case, if we're taking it by my definition, pretty cool. It's going to the right. Equivalence. This is equal to this, and this is equal to this. So this is equal to, if A is equal to B, and only if A equals to B, that's not what this means. This is an equivalence symbol, but they just mess it up. Now here, not belongs to is an element of. Again, I'm putting the goats right up here, pretty cool. Super fun, looks super cool. It is exactly this constant that we were mentioning before. Where did we put it? Here, epsilon variant, exactly. Exists, mediocre. It looks cool, but you can just write there exists a number for which A is an element of complex numbers or whatever. So it's kind of useless. These dots, never seen them before. They're going right down here at the bottom. For all, now this is pretty nice because when you say for all, you're pretty certain. So it's going right here in normal just because it's not used enough. But yeah. Identity, you can use this as an identity. I use it as congruence. So whenever you're doing like a congruence equation, you're trying to prove that a number is divisible by another number congruent to some variable. You use the 3 lines and then you would say modulus whatever your number is. In that case, I would say it's overrated. I don't like it too much just because it's kind of counterintuitive and no one really teaches it to you at school, so you have to teach yourself. But when you do learn it, you know, it's nice to use and it's very well used in proofs. And for that reason, overrated. C tier, I think is just the right place for it. Not trash. Just don't use it. Just say it's not equal to. Next up, factorial. My combinatorics fans are gonna like me for this, but I love the factorial sign. I find it so funny when people write an equation like 5 plus 5 equals, I don't know what it would be, 5 factorial or something, whatever it is, 4 factorial, or something like that. And people will be like, no, it's not equal to 5 or 4, but it is because it's equal to 5 factorial, and people don't know what the factorial sign means. But in any case, the factorial sign is the go. A tier, you know what we knew. Length in meters. So guys, now we're moving on to these, essentially, measurements, units of measurement. Meter. The GOAT. Literally one of the most important metrics ever. Physics work perfectly when you use meters. Physics work perfectly when you use liters. They work perfectly when you use seconds. I mean, it's just so perfect. Physics works the way it works because we have these perfect units of measurement such as the meter. Time in seconds. Unfortunately, guys, it is mediocre. I'm sorry, but the Babylonians, they liked base 60, so they invented seconds. But guys, come on. We should have been using base 10 for seconds. We would have been so much more efficient. And it would have been super easy. Now, mass in kilograms, I do not really like it because often you have to convert it to newtons. So again, I'm putting it in mediocre for a physics context. In other contexts, it might be better. Electric current ampere. I think ampere are great. I don't think they're wonderful. I don't find them particularly nice, but I think they're just fine. Now, a mole, the amount of substance. Now, the thing is, people don't understand how the mole and Avogadro's number correlate with each other, but when you do understand that Avogadro's constant multiplied by the amount of moles will give you the pure amount of molecules. And if you understand that, this will make sense. I'm going to put it right next to Avogadro's number if I can find it. Here, so, there we go. Amount of substance. Temperature in Kelvin. This is beautiful. Absolutely wonderful. A++. I mean, I can't imagine a better unit. Imagine using degrees Celsius in physics, like minus 500. Your entire equation would just collapse in on itself with negative numbers. I mean, what are we even doing? Luminous intensity, unknown, never heard of it. Ooh, radians. Now, I love radians. I do not like to work with degrees. Imagine somebody tells me like, oh yeah, I'm around a circle, I'm at 245 degrees. I'm like, what do you do with that? Huh? You think I could convert that in my head to radians? No. But if somebody told me like, oh yeah, man, I'm at, I don't know, 7 pi divided by 4 radians. Maybe I don't know exactly what 7 pi divided by 4 radians is immediately. But what I can do is do like 3.5 pi's divided by 4 radians. And like somehow get to that value in my head. But degrees are just more complicated. And radians are just so cool. They sound cool. I'm putting in A tier. I love radians. Now, solid angle. If those are degrees, then pardon me, but I don't know them. I don't know what they are. Frequency in hertz. I mean, it's a good frequency. I'm just going to put it in C tier. I don't know what else we'd have to do with it. Oh boy. Forced in Newton's the GOAT, Newton, but I don't really like Newton, so I'm gonna put it in B tier. I just find Newton's like, he's too good, man. He's too good, and for that reason, I don't want to glaze him because he got enough glaze on him already. Everyone's glazing Newton. Why do I gotta glaze Newton? I don't want to glaze Newton. He's glazed enough, man. He's already white as he is. Pressure in Pascal. Pressure, a very simple formula. You just got your force divided by your surface area. Very simple, very intuitive. I'm putting it in normal. Energy in joule. Wonderful. One of the first things you learn in physics, starting 7th grade, energy in joule. Power in watts. I think it's nice, but it's normal. It's not something too advanced. It's not something I can get too excited about right now. But it is something that I am happy about. Power in watt. There we go. I'm going to put this on the same level as joules. People confuse them because they're like, what do you mean 1 watt second is equal to 1 joule? And 1 watt second is not the same as 1 watt. It's like super unintuitive for people, but that's just the way it is. Get used to it. Now, electric charge, Coulomb. I mean, we don't use it much. At least I have not used it much, but I'm also not much of an electricity fan. For that reason, I cannot talk about the actual applications of the Coulomb. I'm guessing there's more when you get into electromagnetism, but for now, I'm just going to put it in overrated C tier. Potential in volt. Ooh, it looks cool. It sounds cool. It's useful. You don't want to get shot by 5,000 volts of electricity, but at the same time, nobody really understands what it means to have potential. When you're talking about electric potential or hyperphysical potential, nobody really understands what it means unless you're a physicist, and it's like regular students don't understand what volt even is. They think voltage is just like the flow, like it's going downstream, but that's not how it works, but no one really understands it well enough to explain it. For that reason, overrated. I just have to do it. Capacitance in farad, nobody knows this, it's going in unknown. Now resistance in ohm. Now I have to say, the ohm, the omega symbol, did we have the omega symbol? I think we did. The omega symbol, it looks great, it looks wonderful. But resistance is such a nightmare. Like, what do you mean you're supposed to tell somebody that in specific circuits, adding more resistance equals less resistance? Like, no student's gonna understand that. For that reason, overrated. Magnetic flux, I mean, unless you have a magnetic flux capacitor, which I don't even know what that means. I know Weber. I thought, isn't Weber like some sort of book company? I don't know. That's going in trash right now. I'm sorry, guys. Luminous flux. What is flux? What is flux? I think I know flux from this one Tesla's. Like Tesla. Tesla had something to do with flux capacitors, and there's some unit of measurement for flux, but I don't know what it is because we're not there yet, guys. I'm sorry. Guys. I'm a self-taught individual. I only teach myself what I want to learn about. If I want to learn about quantum physics, I will teach myself quantum physics. But I don't care enough about electricity or components to teach myself what a quantum flux capacitor is, alright? I'm sorry. That's just not the type of guy I am. Now, radionucleotide activity. I'm sorry that, again, I'm not a radiologist or whatever. I'm sorry. I don't know what this is. How do you want me to rate something when I don't know what it is? I'm sorry, guys. I'm about to crash out. This is ridiculous. Ooh, boy. Oh, boy. I'm about to get angry. Alright, guys. Next up, X. X, the constant. It's wonderful. It's there from the beginning. But it's just too overrated. People don't like X because it's so complicated. Nobody wants to speak about it. I'm going to put it in normal. I find it's a good letter, but I feel like we could have found a better letter. I feel like Y. Y would have been better to have. Because Y, I like Y more than X, because Y comes when you're doing your differentials, Y comes when you're doing your PDEs, your ODEs, your all different kinds of mathematics. So Y is way higher than X. Yeah. And Z is going right in trash, because nobody ever uses Z. When do you ever need a third variable? Unless you're literally doing triple integrals, you don't need Z. Because you're never doing triple variable like algebra. Well, you never need that. You need two. You need your fixed component in physics, and you need the variable of time. You have two. You're done. You don't need more than that. Anyway, now let's continue. Oh, wow. So the function notation, I'm guessing this is the one by Euler. I'm going to put it in S tier because you know my goat Euler. He's the goat. He's the greatest of all time mathematician. Greatest. Function notation, beautiful. I love this. You can have X, you can set for f of X, and you can plug into f of. And it's just beautiful the way it's written. Differential. I don't like the differential standard notation. I'm sorry. Alright? I'm very, very sorry. But Leibniz, what the heck were you thinking in writing that the differential or the derivative with respect to x by writing it in a fraction? So students are going to think that it's a fraction. And you make it worse that when you do u substitution, you multiply by dx, and so people think you can just treat it as a fraction, even though it's just a one-case scenario. Do not treat the d with the d divided by dx as a fraction. It's not a fraction. Please get this out of your head. D with respect to x is just saying that we're taking the derivative with respect to x. We're not saying that we're dividing d with dx. That's not what we mean. It's just a notation. The partial derivative looks beautiful. It looks so fancy. It looks so cool. And it's so simple. I mean, partial derivatives are just basic derivatives. They just have partial parts. You think it's difficult, but it isn't. I think ordinary differential equations are harder than partial differential equations. At least they seem like it in the beginning. And I never went too deep into it because at some point I realized it's just Ansatz and just guessing, and I realized there's not really much math behind it. Once you understand the intuitive part of it, there's no point in going deeper into it unless you're like an engineer and you have to do it. Oh boy, Lagrange notation. This right here is legendary. I do not want to see any other notation being used for derivatives other than the Lagrange notation. It's beautiful. You can write a big F if you're saying you want to take the antiderivative. You got F prime for your first derivative. You got your F double prime for your second order derivative and F triple prime for your third order derivative. You can even write Fn of, where the n stands for the order of derivative that you're taking. I mean, it's just so adaptable. Because imagine writing d squared, like the derivative with respects, it's like d divided by, it's like d squared x divided by dy, or d cubed x divided by y. It's like people don't even know what's going on. That looks so absolutely atrocious. But with Lagrange notation, it just looks so beautiful. Alrighty, Newton notation. Ugh. Newton, what were you thinking? Dots. I mean, I guess it's not that bad. It's not that bad. It's way better than the regular standard d of dx notation, but still. I mean, it's very clear that Leibniz did a way better job than you, so sorry, Newton. Alright, now come the big boys. The integral. S tier. Where did you think, guys? Where did you guys think that the integral, where did it go here? Where did you guys think the integral was going, huh? The integral is one of the greatest mathematical symbols of all time. The most aura. On TikTok, the edits of the integral sign are unmatched. The functions of the integral are unmatched. Calculating the area under a graph is the most important part of calculus. You cannot tell me otherwise. Bro, do not try to tell me that analyzing like limits or derivatives is more important. Integrals are infinitely more important across the board. I'm sorry. Closed integrals, I find them to be useful. In some cases, whenever you're working in the complex plane, sometimes you want to use your contour integrals, but I find that they're just very rare to use and they're not very practical unless you're like an engineer or you're doing advanced physics, and the integral is just uses all across the board. Whether you're in maths, statistics, economics, the integral is used everywhere while the contour integral is not used across the board. For that reason, I just have to say that the integral is just much superior. So the closed integral is still pretty cool, A+ tier. Nabla? Unknown. Who's ever used this? Oh wow, I didn't even know we had a capital sigma. If we did that, I wouldn't have put the sigma so high. But the capital sigma is one of the goats. Where do we put it? I think we put sigma somewhere here. We're going to put capital sigma right here in beautiful A++. Guys, you just got to understand. The capital sigma is the #1 mathematical summation. I don't want to be writing down A plus B plus C plus D. No, you want to write the sum from n equals 1 to infinity of an, where n is equal to whatever you're going up, and a is the letter that is responsible for that in the alphabet. And then you would have A plus B plus C plus D, and you would be able to do that all the time, and you wouldn't have to write it all down. Like, imagine trying to write down recurring. 1 plus 2 plus 3 recurring forever. Like, no. What you want to do is write the n equals 1 to n equals infinity of n. And then it's just going to go through. It's going to be 1 plus 2 plus 3 plus 4. So the capital sigma, super important in mathematics and physics whenever you're iterating. Capital pi, I mean, it's nice because, you use the capital pi for your, for just like, it's the same as sigma, but instead of doing it for summation, you do it for your product. So for multiplication, it's cool, but you don't use it as much and people don't speak about it as much. So I'm just going to put it up here in A tier. But there's one fun fact is that if you put it on 1 and you let it go up only to the number of x, you're basically just doing a factorial but backwards, and you still get the same value of that factorial. I thought that's just funny to say. Next up, the direct sum. Now we're working in linear algebra, and we're working with mathematical notation, not just in with system gates. I'm not sure if they use them in regular IT, but from what I know, we use them in quantum physics for for transferring information using superpositions. The direct sum, I don't really know much about it. We didn't use it that much in quantum physics. We mainly multiply, so some we don't know much about. I'm just going to put in C tier because it looks pretty cool, and I'm sure there's a lot of very important uses for it. Now the tensor product, very, very important. You need your tensor products if you're going to be multiplying multiple sets together in set theory. You need the tensor product. If you're multiplying set A with set B, you got to get every single combination out. But it is set theory, and set theory is not that popular. I'm going to put it right next to overrated. Now I think that the direct sum might not be what I thought it was. I'm pretty sure they use the same symbol in logic gates, but I don't think that these are logic gates. I think this is just the direct sum of taking two sets, like also set theory. All right, now the transpose. All right, so now we're getting to very complicated theories. So basically what the transpose is it's basically when you take a matrix and you invert its rows with its columns. So if you have a matrix such as, let's say you have a 3x2 matrix, so it's 3 columns and 2 rows, and it goes like 1, 2, 3, 4, 5, 6. It would be like 1, 2, 3, 4, 5, 6. What you do is you rotate it so it becomes long, and it's like 1, 2, 3, 4, 5, 6, like that. So you basically transpose it. And so this is an operation we do in linear algebra, and it's useful, especially if you combine it with the conjugate transpose, which is inverting the complex part of a complex number, the imaginary part. The complex conjugate and the complex transpose together, the complex transpose the conjugate transpose is very underrated. It's super useful. So if you have not learned anything about it, it's very nice. You could do some research on it. Next up, infinity. So infinity is nice. You have it in your integrals, but when you're doing it for your integrals, obviously you just have to calculate the limit of your expression and then integrate the expression. Obviously, if it diverges, then you don't have sum under it. It's going to just become whatever it diverges to. But if it diverges, I mean you don't have a sum underneath. You don't have an area. But it's super useful also in limits. So you do get it already in your beginning phases of calculus, not just in the end. I think it's beautiful. Super useful. And for those who don't know, you can have a plus infinity or a negative infinity. That's also pretty nice to know. The aleph, it's alright. I mean, it looks nice, but I don't even know what it's really used for. So we're going to put it overrated in C tier. And finally, Euler's number. Oh boy. This is the GOAT. This is the GOAT. Euler's number. S tier. I love my boy Euler, guys. He's the GOAT mathematician. So how dare I not put Euler's number at the very top of the list? So to summarize, in our F tier, we have things like theta variant, pi variant, divide, not, Newton notation, and z as an algebraic variable. And at the top, number 1, lambda. It's going. My number 2 symbol is going to be the integral. My number 3 integral is going to be Euler's number. My number 4 is going to be Lagrange notation. And number 5 is going to be psi because of quantum physics. Alright guys, I'm going to show you guys my list one more time. This was my ranking. I hope you guys enjoyed the video. I've been using a lot of energy. I'm not feeling too well, but I'm thinking about uploading more, guys. So thank you all so much for watching this video, and I'm going to see y'all in the next one. This is Doom. Peace out.